the principal component analysis which we like to cover today, that will be very useful for us while we will be designing the biometric system. That principal component analysis, it has the two major roles. First role is that it gives you the indication about the patterns of the data. And second thing you will be getting that sometimes some informations or the patterns of the data, they are not useful. They are related, closely related. So you why to consider those patterns? You can easily suppress them. So basically, a principal component analysis will be useful when you want to reduce the dimension. And by the word reduce the dimension, it means that number of feature elements you like to consider will be less. Okay? So that is the basic. So generally, by seeing the data, you like to see that what is the pattern in that, right? Are they maintaining certain relation, or is it there is no relation exists, randomly distributed? So these patterns you need to know. Now once you need to know these patterns, you want to highlight these patterns, right? Highlight the pattern means that how much similarity there exists, how much dissimilarity there exists. That is the issue, right? If there exists a too much dissimilarity along a pattern, that means that will give you some features, because our aim is to get certain unique features against an object. So to get the unique features against the object, that means you want to know how much variability you have within in a particular pattern. So that is the aim. So the first one is that you want to find out whether there exists a pattern or not. Second part is that if there exists a pattern, then how much similarity or how much dissimilarity is there. If the similarity is too much similarity exists in one pattern, that means that pattern is not useful parameter or characteristics to consider as a feature element. Now this pattern you can visualize if you plot it. Now plotting is possible when you have one dimensional, two dimensional or three dimensional, but more than that you will not be able to visualize whether there exists a pattern or not, right. So that is the main problem. Problem is that you can think what for I should use the PCA once I know the pattern, but pattern is visible only for the smaller dimension. For larger dimension you have to take the help of PCA. PCA also, as I told you, also help you that I want to reduce my dimension by discarding those features which are having the most similar behavior in a pattern, right. So suppose I have the data of n elements, each element containing the p variables of p variables. P variables means that p characteristics, p dimensions, right. So you have the p dimensions and you have n observations. So this is your data set. Now through the PCA you can reduce the data set into n cross k, where k contains topmost patterns having the larger variance or variability. That is the idea. So what you can see that you have the original matrix A. Now A of size n cross p, I am reducing into n into k. Obviously you are losing something, right. So the term is residual variation. It is the information in A, but that is not in your n cross k area. That is known as residual variation. This residual variation should be as minimum as possible. That is the aim. Now that gives you the indication there exists a trade-off relationship between the clarity of representation and oversimplification. By the term clarity of representation means that whatever data you have, you must be able to get proper representation So, if I have the matrix A itself n cross P, obviously you will get the same matrix whatever originally A, everything will be there. Now, if I reduce to n into k, so some information will be lost, but you are simplifying. But by the process of oversimplification, you may lose certain information. So, there exists a trade-off relationship between these two. So, you have to choose such a k, so that you get the maximum information, but maximum reduction of size also. That is the problem. Is it clear? Now, okay. Now, this is very well known method in statistics, where you need to reduce the dimension to analyze it, because they have the multi-dimensional things. So, need to reduce. Same thing will happen in our case also. Well, we will be covering our biometric system. So, it takes the data of size n cross p, because p dimensions and n objects you have, and they are correlated, right. That if you have one x1, corresponding value will be there, x1 1, x1 2, x1 3, x1 p. So, corresponding values will be there. But what we want to express it into the uncorrelated dimensions, which is we want to plot it in the direction of principal axis, right, and that has to be expressed in the form of linear combination of those variables, right. How to do it? We will discuss this, and then we want to pick up the top k elements, top k principal components. Now, what do we mean by top k principal components? Those principal components you are selecting are having the largest variance, k top variances. So, this is about the definition of principal components. This is the data you will have. So, what happens that you have the point cloud data. Point cloud data means that you have the point which is represented by p variables or p dimensions, and here one is variable x1, another is variable x2, like that p dimensions are there, these points are there. And the top centroid, I think you know by now in statistics you have heard centroid. Centroid is nothing but the mean of the variables, each objects in all dimensions, right. So, xi bar is equals to 1 upon summation. So, xi bar is equals to 1 upon n summation over xij, j is 1 to p, right. So, centroid of the points defined by the mean of each variables, and similarly you know the term variance. Variance is nothing but that sums of square of deviation of each variable from mean, and then you are taking the average. You should have taken 1 by n, but to get it, you remember why it is 1 by n minus 1? That nth term is degrees of freedom is n minus 1, so we are dividing by n minus 1, sum of square. So, degrees of freedom is n minus 1, that is why we are normalizing by n minus 1. The next term you will be using the covariance. You remember the term covariance? Covariance is nothing but you want to find out the degree of correlationship in the linearly correlationship between the two variables, right. So, it is equal to summation xim, xi bar, xjm minus xj bar, and 1 by n minus 1. The Cij is the covariance variable relationship between I and j, and this m is sum over all n objects and value of variables object xi. This is the average of this, and similarly the average with respect to the variable j. So, now the term I think you know what is the term is eigenvectors and eigenvalues, and its application you cannot forget. You may forget the formula. Remember that why I need that this is required not only for biometrics, you may require this thing for future also. Now, these eigenvectors and eigenvalues are basically depend on the some certain transformation or it will give you certain another vector. That is the thing. Suppose you have n cross n observation matrix, that whatever we have considered, you have n cross n, right, that n variables and n dimension, it is you have n cross n, and you have a vector say A, it is also n cross 1. So, if I perform this operation, what I will get? I will get another vector, right. Okay, this some symbol is there, no vector arrow mark. I assume that this is vector because generally we write in bold letter, but here there is no scope of writing. So, this is another vector. Now, these two vectors are parallel. When I can express this is multiplication of some scalar multiplication of A, right. So, these two are parallel when this can be expressed as scalar multiplication of A, or one can be expressed in terms of the other one by multiplying by something, some real number. So, that means what? X A can be expressed as lambda A, right. Then you can tell these two vectors are parallel, right. And if you can express this when lambda is some real, then this A is known as eigenvector. This A is known as eigenvector. What it means? Basically, a point is here and this is origin and it gives the direction like this. Now, lambda is a scalar, so it will give you the increased form, right, or here, right. So, it is giving only the direction of the element of elements with respect to the origin, that is the vector. And what is this lambda? Lambda gives you what it means. Once you transform this A to this bigger one, what is the deviation, what is the dispersion, what is the variance? Once you move this one to another transformation, then there will be a dispersion, variation. What is the variance with reference to that pattern? That will give you the lambda. Okay. So, we will be looking for the larger value of lambda for our principal components. Largest value of lambda will help me to detect that yes, this is a principal axis. So, this can be written as so basically you will be writing this is determinant of x minus a lambda I equals to 0. That is the thing you have to. Now, you solve it, you will be getting the values of lambdas, right. Say, let us consider 2-3 small examples. So, A dot A is a 2 1 1 2 0 1 and so it will becoming what 1 2. So, this is you observe that these two are not cannot be expressed in terms of this, right. So, this is not an eigenvector, this is not an eigenvector. But if I consider 3 minus 3, So, this becomes lambda is 1 and this can be expressed A in the form of A. So, it is an eigen vector. Now, tell me what should be my A, so that A is an eigenvector, right. So, one possible could be 3,2, is it correct one? So, we will come later on how to find out, but first this is a just trial and error method we are using. So, lambda is 4 and so 3,2 is your eigenvector. Now, how to find out this? You see here I have just put the value and I have told that it is an eigenvector and this is. Now, in order to find it, you have to find out what is your x. X is 2, 3, 2, 1 and so you have to find out x minus lambda I is nothing but 2 minus lambda 3 2 1 minus lambda, right, because I is the identity matrix. So, you will be writing this. So, determinant of x minus lambda I 2 minus 3 lambda plus lambda square minus 6. This has to be 0. Lambda square minus 3 lambda minus 4 equals to 0. Lambda minus 4 lambda plus 1 will be equal to 0. So, this gives you lambda 1 equals to 4 and lambda 2 equals to minus 1. So, you got the 2 eigenvalues. Now, you have to find out what is your eigenvector. Now, you have 2, 3, 2, 1 and x y is equals to 4 times of x y. See, this is the things you have to find out, right. This you have obtained only this part lambda, but not the eigenvector. You have to find out what is your eigenvector. So, this gives you 2x plus 3y is equals to 4x and 2x plus y equals to 4y, and this gives 3y equals to 2x, right. So, once you want to find out the principal x's, so it will be x line, right, y equals to x form. So, this will be possible only when it is 2 and 3. Oh, sorry, this is 2, this is 3 and 2, right. 3 into 2 is 6 and 2 into 3 is. So, this is the only way you will be getting this line. So, this is your x y, that is your eigenvector. Suppose I have x 5, 2, 4, minus 3, 6, 2, 3, minus 3, 1. Now, can you find out what is this eigenvalues and eigenvectors? See, it is not essential that matrix should be square matrix, but after multiplication you must get the square matrix, and the minimum dimension will give you the that many number of eigenvalues, right. That means, the size of this will give you the number of eigenvalues. That means, number of dimensions will give you the number of eigenvalues. Here we have considered is the 3 cross 3. Now, can you find out the first you find out the eigen values and then you find what is eigen vectors. How many lambda you will be getting? First you tell me. 3. So one of them should be at least correct. If one is correct, remaining 2 will be correct. I can assure you. Is it okay? This line? First you check this line. If it is correct, then you expand. That is 5 minus lambda, it will be 6 minus 7 lambda plus lambda square plus 6. So it becomes 12 plus 3 times. What is the final equation you got? Tell me. Let me finish first, otherwise. So you are getting lambda cube minus what? Minus 12 lambda square, then plus 41 lambda 42. And this will give you lambda 1 equals to 2, lambda 2 equals to 3. Is it right? 2, 3 and 7 you told. Lambda 3 is equals to 7. Right? Hopefully it is correct, right? Now what is the eigenvector? Find out one eigenvector. You take 3, lambda 2 equals to 3, and then you tell me the eigenvector. Five to 4. 6, 2, was it 5 or 3? 5. Then what about relationship between x1 and x3 or x2 and x3? Hmm? 3? 3x1 plus x3 2x3. Hmm? 2, 4 minus 3. How 2, 4 minus 3 होगा? What is 2? x1 2, x2 4, x2 4. How did you get? Hmm? 2, 4? So what, that will be that 2, 4 minus 3. Let's solve the equation. So if you put this value, you can find out the result is coming. So this is your background of eigenvalues and eigenvectors. And what I want to tell you that eigenvector gives you the direction with respect to the principal axis, and eigenvalues will give you the variance with respect to that pattern, that principal axis. So given the n p-dimensional elements of n observations, your aim is to rotate the axis point to a new axis point. That axis point is termed as principal axis, which satisfies the following properties. First one is that it should be ordered in such a way that the principal axis has the maximum variance. Then the axis 2, which is the next maximum variance, and so on. So you will be getting, since it is a p dimension, so you will be getting the p principal component, p principal axis. But you have to arrange in certain order, increasing or decreasing order. Highest one will be your principal axis 1, then next one, and so on. And also you have to select this axis in such a way that they are perpendicular to each other. Right? The principal component I is perpendicular to principal component 1, 2, 3, and so on. So principal axis should be perpendicular to, so that is they are on J. Now PC2 computation is the important thing, that PC2 is also similar to whatever you obtain in the case of variance. Here also it is a Euclidean distance, but in distance it gives you the measure of dissimilarity, how much it is deviating. And based on this dissimilarity, you decide whether this component or this component is getting the higher preference than the other one, because the variability gives you the uniqueness characteristics. So more the variance, more the dissimilarity, you will be choosing it first, right? And there is, out of, suppose you assume that it's a p dimension and you observe that all p dimensional activities may not be, there are some cases you find that very closely similar. You do not have to consider that one, but you have to select in such a way that total dissimilarity value should be near 100, right? Or some of the coverage, some of the informations, characteristics of the image, whatever you are considering within the k dimension should be as near as possible to the original image. That is the close representation, or easy. You have to have the original representation. You may not get the exact representation, but as near as possible, keeping as many as dimensions reduced you can do on your image. So if you have the two variables, nobody does the PCA. Just you find out the correlation coefficient, you can easily find out what is the pattern. Right? You do not have to do that. But more than 2 dimension pattern, for pattern analysis, you need to do the principal component. And as I told you, that principal gives the direction of maximum variance in the p dimension, and then you consider the PC2 with the condition that this is perpendicular to PC1 and so on. So in this image, first you will be getting the direction this one, and then with reference to PC2, and then you rotate the image, so it will maintain the property of all the things. How to obtain the corresponding coordinate of this value with reference to PC1, you will be discussing later on, right? So what is the formula, or what is the algorithm? First let us have to find out how to find the maximum principal component. That is the first one. Then the second one, third one, and so on. Right? Suppose you have the n observations, x, x1, x2, p dimensions. This is a vector. Right? So first principal component is defined by Z1 equals to A1t transpose of A1x, and which is nothing but summation over I1 to P x1i AI. Now, what is not known? This you have to find out. This vector, this eigenvector you have to find out, such that the variance is maximum. Variance of Z is maximum. That is the problem. Right? Is it clear? So your aim is to obtain the vector A in such a way that variance of Z1 is maximum. Now, can you recollect here, it was a 3-dimensional, that's why we could solve this one. But if it is n-dimensional, how we could have solved it? Because determinant finding is a very difficult problem, right? In n-dimension. What will be, how can you solve? Any idea, any word, any term? I will not ask you to solve it. And moreover, you know that PCA and other things, their ready-made routines are available. So, these are only the conceptually should be clear, and other part is that you just call PCA and you will get the results. So tell me, can you recollect how to find the determinant or find the values of solution of x minus lambda equals to that one? I want to find out the eigenvalues. How can I find it? Any idea? X minus lambda equals to 0. You want to find the solution of that. There is a term, singular value decomposition, SVD, right? So please, I'll try to understand what is SVD. That is the only thing you do yourself, because now what happens the next? If I want to find out the kth principal component, I will be finding the zk. Same way, AKT x. Now you have vector, you have to select this vector with the condition that variance of zk is maximum, but of course must be less than z1, z2, z3, zk minus 1. Right? So, and also the covariance between the zk and with the z1, z2, each of them, that should be 0. Because they should be, as I told you, that it should be perpendicular to every other axis, and this is the condition of orthogonality, so that should be maintained. So this part already I indirectly told that you are not selecting all the p dimensional variables, you are selecting k of them, k best of them on the hyperplane. And this k principal component 1 to k represent the maximum possible variations in the data, right? And that is definition of maximum possible variation is nothing but we have considered the Euclidean distance. So you could have used the simple covariance matrix on your data, but there is a little problem because that their units, their variables, the p-dimensional units may not be the same. So that is the issue. If you know that their units is same, then directly you can obtain the covariance matrix. Another thing is that you must ensure that there is not too much dispersion, or not too much variance is not that high, because the high variance will create or will have the positive impact towards the principal component, higher principal component. So best way is that you normalize it. How to normalize it? Just x minus x bar divided by sigma. So in that case, x minus x bar divided by sigma, if you do it, then all the dimension, your mean will be 0 and standard deviation will be 1. Am I right? Because if you remember that if you have the variable x and x bar is the mean and sigma is the standard deviation, then x minus x bar by sigma obeys the normal distribution with 0 mean. Obeys the distribution 0 mean and standard deviation 1. Am I right? Yes. So that is the thing. So we generally normalize it to 0 mean and unit variance. Now if you have the normalized elements or of subjects or objects of n p dimensions, then your covariance will directly give you the correlation, right? Covariance, because it is a normalized one, x minus x bar divided by sigma. So if I just covariance matrix will give you the information of whether there exists a correlation between any two variables. And also that standard deviation, also each variable will have the standard variance 1 because you have already divided by sigma. So variance will be always 1. Now, if I have the covariance matrix, that means Cij is the covariance between I and j, then, and if my variance is not normal, is not 1, then correlation matrix Rij, that correlation between I and j, becomes Cij divided by square root of Vi and Vj. Am I right? Yes. Now this can be rewritten that first you obtain the cross product of matrix of variance and covariance, and if you have the cross product, what happens? The diagonal elements will be the always variance, and this will give you the correlation or covariance between x1 and x2. This is covariance between x2 and x1, and so on, right? And this will become always a square matrix because you are making x and xt. The diagonal elements will give you the variance, and this will give you covariance, and these are symmetric. Is there anything else here? So this can be in matrix notation. This can be written as x is prime x, because that will give you the covariance matrix where x is a normalized elements, and your size n cross p. Right? Otherwise, you could have written x prime minus mu divided by sigma into, like that you could have written. But this is a normalized variable, so you do not have to write those things. Now remember the trace one. Trace of a matrix is? Huh? Some of the diagonal elements. Some of the diagonal elements is the trace. It is a very useful property in PCA or relationship with the values of eigenvalues. Now you have the, here is notation S, there we have written X. That is the determinant. You have to find out the solution of these characteristic equations, and usually we use the singular value decomposition technique to obtain the values of lambdas. And this eigenvalues for this one, that eigenvalues is becoming lambda 1 equals to this and lambda 2 equals to 3.03. You observe the sum of these lambda values is equal to sum of the standard variances. That means trace of this equals to trace of that. Now what happens? That you got eigenvector from these eigenvalues. Now each eigenvector consists of how many variables? It represents the consist of p values, right? P values will be there. And it also gives you the contribution of each variable to the principal component, because that will be, that will provide you the principal axis, and this, which refers to the original xy values, x values, it has certain contribution on it. So eigenvector consists of p values which represent the contribution of each variables to the principal axis, and they are uncorrelated as I mentioned. So their cross product, this into this plus this into this will be 0, because they are uncorrelated. Now this, once you know X is given to you, X is given to you, X is the whole matrix, original matrix, and U is just how you obtain the eigenvector, right? So you need to know that what will be the mapping function for each X values into the principal axis, right? This is known as scope. So coordinates of each object on the kth principal component, which is known as the score on PC kth principal component, which can be computed as zki equals to, this is known 1k into x1i. These are also known u2k, because this is the vector, eigenvector, and this is your original matrix. Now, eigenvector, it has given you the P cross K matrix of vectors. How are you getting that? One vector is of size P, right? There are K such vectors. So the whole, all these things, you have one vector of size P, then another vector of size P, like that there are K such vectors. This form a matrix. That is your eigenmatrix. So you have X is of size n cross P and U is of size P cross K. So you will be getting Zki, the corresponding value of on the, with reference to the principal components. Now you know the lambda values. Lambda is nothing but the eigenvalues, lambda 1 and lambda 2, and you also know the trace. Trace is nothing but summation of what? Lambda 1 plus and lambda 2. Now, that what is the information you are getting with reference to PC1, right? That is nothing but the difference or dispersion or variance of respect to the first component eigenvalues divided by sum of all the lambda values. Right, that is the coverage or informations you are getting with reference to the first principal component. That means that 9.8783 divided by 12 on this is 76.5% information are being carried out with respect to the first principal component. Now, if I consider, and second principal component here, since you have the two principal components, so second will be the remaining of this element, right? Now it may so happen that there is a three principal components, and now you find out how much information you are getting through lambda 1 divided by lambda 1 plus lambda 2 plus lambda 3, then lambda 2 by lambda 1 plus lambda 2 plus lambda 3. If you take the sum and you are finding that they are coming 99%, that means that 99% of information you will be getting if you consider only these two components. And if you reduce the or you do not consider the third one, right? So this is also again another, because I will correct all of them because of this design problem. Now, if I have the variance covariance matrix with respect to your principal component, since they are orthogonal, they are uncorrelated, so these elements will be 0. Only the diagonal elements will contain the variance and covariance part will be 0 because they are not related. They are not correlated. So this is your variance covariance matrix. Now, I have to, once I know the eigenvectors, you have to project it, right, with reference to the principal axis, how it looks. So you have the V is an eigenvector matrix of size P cross P, where each row contains the eigenvector, right? So first row contains all the eigen elements, or all the first row contains the large eigenvector with the largest dispersion, largest lambda value. Second row contains all the eigenvalues all the elements of the eigenvector having the second largest lambda value and so on. Vk is the support, top k elements, top k rows. Vk is the top k rows because I do not want to consider the remaining one. So Vk is the top k rows. And A is your original matrix, n cross P. So A is original matrix and Vk transpose is the top k rows of the eigen matrix. So if I multiply these two, I will be getting X, which will be your projected matrix. Right? Now, suppose I have the projected matrix. I want to see whether I can regenerate back or I can get back my A. So, of course, you will be writing X Vk transpose inverse should be equals to A. Right? So, Vk transpose inverse is also Vk because Vk into relation is like this. That is the thing. So you can always tell that this can be replaced by V. So whatever value you will be getting, that need not be exactly A because you have suppressed some of the informations, but it is nearer to A. Right? So your aim is to obtain such a V such that after projection, after regeneration, I should get the near value of A. Right? So that K is important. That K is the requirement. Now what assumptions we make? The most important assumption is the relationship among the variables must be linear. Otherwise, you cannot have this principal axis concept because if it is not linear, right? If it is non-linear, then this principal axis you cannot determine and everything is gone. Our whole idea will be gone. So you must be able to express in terms of that something is equals to A into lambda plus something into lambda 2 plus something like that, right? So this is the assumption is that this relationship must be linear among the variables. So anything you want to ask on this? So we'll consider one example where phase is one thing where it has been used, PC has been used intensively. So we'll consider that one while we'll be considering the phase biometrics.